In this video, we will talk about problem E, count paths from Codeforces Educational Round 162. You are given a tree. You need to find out the number of simple paths such that the terminal vertices have the same color and the internal vertices do not have the color present on the terminal vertices. Let us start with a simple problem. You are given a tree that contains white vertices and black vertices. A downward path is a path that starts at any vertex and only goes down in the tree. This downward path is called good if the last element of the path is a black vertex and all the other elements in the path are white vertices. Your goal is to find out the number of good downward paths in this tree. How do we find out the answer? Notice that the final downward path has to begin at some vertex in this tree. It could either be this vertex or this vertex and so on. So we can define count of u as the number of good downward paths that start at a particular vertex u. Then the final answer would simply be summation of count of u for all the nodes in the tree. All we need to do is figure out a strategy to compute this count array. If a vertex is black, then the number of good downward paths starting at this vertex is exactly equal to 1. Why? Because a black vertex indicates the terminal element of the path. Therefore, you cannot go here or here. So, whenever we encounter a black vertex in the tree, we will simply set count of u is equal to 1. Now, what happens when you encounter a white vertex in the tree? For example, what happens when you encounter this vertex? We need to find out the number of good downward paths that start at this vertex. But if it starts at this vertex, what can the second element of the path be? Of course, it will be one of the children. And if you remove a white vertex from that path, the first vertex in the list, the resulting path will also be a good downward paths. Therefore, if we can simply find out the number of good downward paths that start at any of the children, then we can go to that downward path and prepend this vertex over there. For example, this is a good downward path for this children. So in this path, you can simply prepend this vertex 1 to get this path. Another example, this is a good downward path for this children. So you can take this downward path and prepend this vertex 1 to get another good downward path that starts at this vertex. Therefore, count of u for a white vertex would be equal to the number of choices of the downward path that each children has, right? It would be the sum of all of them because this is the first element of the path and you are allowed to freely choose the second element in any of the children. So that's why count of u would be equal to sum of count of child. Since this recursion of node u depends on child, we can simply populate this count array via a simple DFS call. That is, by the time we arrive at node u, we can assume that all the count values of the children will be populated. Then we can simply sum them up to get the count value of a white path. And of course, the final answer would be the sum of count of u for all nodes in the tree. The code is pretty simple. We set count of u to be 1 if u is a black vertex. Then we recursively populate the count array for all the children And then if it was a white vertex, we sum up the choices available to us because we are freely allowed to move into any of the subtrees that we want. You can submit this solution in the CF step Codeforces group. Suppose you have the same tree with white and black vertices. Now, instead of finding only the good downward paths, we are interested in finding out all the paths such that the terminal element of the path are black vertices. For example, this is one such path because 6 and 3 are black vertices. Another example is the path from 4 to 10 because 4 and 10 are black vertices and no other vertex on this path is black. Your goal is to find out all the paths where the terminal elements are black elements. Another example could be this path because 3 and 4 are black. Now notice that in a tree any path will look like this. That is, there will be one vertex from which the path will rise up to some particular vertex and then it will fall down to the destination. Either this or it can simply be a downward path. That is, this path rises up but it doesn't fall down again because this is our destination. So you can pause this video right now and confirm that all the paths in this tree that you see on this screen does follow this pattern. And in fact, this vertex, that is the point after which we start going down, is called the lowest common ancestor of these two vertices. And even if we do not go down again, we still call this point the lowest common ancestor of these two vertices. Let us define a path to be good if the terminal vertices of the path are black vertices and all the internal vertices are white vertices. Now let's define dp of u to be the number of good paths such that the terminal vertices of those paths have LCA equal to u. Notice that any path will have LCA that belongs to the tree. So if we sum up all the dp values across all nodes, we should get all the good paths that we are looking for because all the dp values are disjoint. If a node is black, then it means that it is already one of the terminal vertices of the path because as we saw in the previous slide that LCA will always be white, it will only be black when the path is a straight line. So if a node is already black, we can prepend this node to all the downward paths that end at a black vertex. And in fact, this is the first problem that we solved in the video and we stored the computation results in the count array. So if a node is black, we just sum up all the count values for the children, that is all the downward paths that start at the children, and then we will go ahead and prepend this node to get a path where the LCA is equal to this node and the path has terminal vertices black. Now what if the LCA is white? How do you compute the DP value in that case? If you go back to the previous slide, you will notice that the LCA being white is simply a combination of two downward paths. That is, you pick a downward path in one subtree that ends at a black vertex and you select another distinct subtree, pick a downward path that ends at a black vertex. You take these two downward paths, insert an LCA in the middle, and then you will have a path that starts at a black vertex and ends at a black vertex. And you can see that you can do this operation for any two distinct subtrees, and you will always have a path that starts at a black vertex and ends at a black vertex. So eventually the problem boils down to finding out efficiently the number of downward paths that start at one of the subtrees, right? Then we can pair up any two distinct subtrees to get a path that makes it as the LCA. For example, how do you figure out that this is a valid path? So if this is the LCA, then this is one valid downward path in this subtree, and this is one valid downward path in this subtree. So you can pick these two paths, insert LCA in in the middle, and then you have a path that starts at a black vertex and ends at a black vertex. The only condition is that both the subtrees need to be distinct, right? Because they cannot be same, because the LCA is white. If the LCA is white, how will you introduce two different terminal vertices with black color? So dp of u would simply be the sum of product of count x and count y, because count x represents the number of downward path in one subtree and count y represents the number of downward path in the other subtree. If you concatenate these paths, add LCA in the middle, you will have a path that starts at a black vertex and ends at a black vertex. Similarly, if you want to figure out this path, you will pick one path, one downward path here, one downward path here, and then you will concatenate them by inserting an LCA, a white LCA in the middle. Then you sum this up over all subtrees or all children, and you will have the answer. For the code, notice that this is the exact same code from the first problem that computes the count of downward path that start at a particular vertex and ends at a black vertex. Once we have done the computation of all the children, we store it in a vector. Then if the LCA is white, as we discussed, we will iterate over all the pairs of subtrees, all of distinct subtrees, and then we can concatenate these two paths independently by inserting an LCA in the middle, right? But if the node is black, then we know that the LCA is black. It means that this is a terminal vertex, so it can only be prepended to a downward path. So that is why we simply add the count array for the children. The time complexity of this code is n square because of this nested for loop. The most expensive operation is computing the sum of pairwise product. But if you think about it, it really doesn't have to be that expensive. If I give you n different numbers and I ask you to compute the sum of pairwise product, would you still take O of n square time? It is actually very easy to optimize it, because let's say that you define a strategy wherein every element will be paired up and be multiplied with the element on the left. So A will not be multiplied with anything, then B will be multiplied with A, C will be multiplied with both, D will be multiplied with this. So you can see that to compute the sum of pairwise product, it is enough to compute the prefix sum and then multiply that element with the prefix sum. That should still give us the sum of pairwise product. And this is a very common technique if you have been in the competitive programming scene for a while. If we implement the prefix sum strategy, then we can iterate over all the choices in increasing order and multiply each choice with the prefix sum of the previous element. Now the time complexity of this code is O of n, which is enough to solve this problem. But we would still like to refine the code a bit. Currently, we are storing all the choices in an array, and then we are doing operations independently on that array, right? Because we We treated it as a new array, and then we figured out that okay, we can now apply the prefix sum technique to do the optimization. But we want to reduce the amount of boilerplate code that we have for pushing into the array and then extracting it out and then doing the computations again, right? So to simplify it, we will not store it in an array anymore. We will simply do the calculation inside this for loop. After doing all the computations in a single for loop, the code becomes pretty short and simple. But the goal of the last exercise was not just to make the code short. I wanted to show you a different perspective using which we would not even have had to go into that prefix sum optimization route. All the code that you see over here, right? This was derived from the manual combinatorics that we applied on all of the children. But if you take a closer look, you will see that you do not even need to consider all the children and derive the formula at once. You can do it incrementally. So what is happening over here? You are iterating over the child and then you are computing all the count of child. So this prefix sum variable, it denotes the number of ways to select a downward path in all of the subtrees that have been seen so far. So as soon as you see a new child, you can decide that you want to keep one downward path in that child and the other downward path in any of the subtree that has been seen so far, right? So that is why you increment dpu with prefix sum into count of child. That is this many choices to pick a downward path in the incoming child and this many choices to pick a downward path in all of the subtrees that have been seen so far. So in a way, this prefix sum encodes the history of the children that have been seen so far. And if you look at it from this perspective, now you don't have to think about 10 different children anymore. You can just visualize it as X different paths are available in the subtrees that have been seen so far, and this many paths are available in the incoming subtree. So there is this many ways of combining them, right? And this is intuitive as well, and if you start thinking in this manner for DP problems, you would not need to go the combinatorics route. With the latest interpretation, you do not need to store the count of all the children at once anymore. You can do the addition of children in an online fashion. That is, children can be incrementally added to the tree without you worrying about how many children are there. So for example, when node 5 or basically the children 5 enters into the tree, the prefix sum would store the possible ways to choose a downward path in all of these subtrees. So that is why you can simply multiply that by the number of possible ways to choose a downward path in this subtree. And therefore you can keep on adding as many children as you want. Using the techniques discussed in the video, how do we solve the original problem that appeared in the educational round? That problem had n different colors instead of just black and white. However, you can still use the same algorithm described in this video by invoking it n different times, and each time you treat color C as black and all elements that are not equal to color C you treat them as white, and then you sum up the answer for all colors. You will get the answer for the original problem. Of course, the time complexity would be O of n square, which will not pass the original constraints. So I have created an easy version in my Codeforces group. You can submit your O of n square solution over there. As for the intended solution, it uses the small to large trick, but to even use small to large trick, you should be comfortable with the O of n square DP solution. And that was the goal of the video, to make you comfortable with the O of n square DP solution. Because once you are comfortable with that, only then can you learn and utilize the small to large trick. I am intentionally not covering the small to large trick in this video so that you don't have to learn a lot of things at the same time. I have added all the problems discussed in this video in the Codeforces group, and I have also added some practice problems on DP on trees. The code, slides, the contest link and all the other relevant materials for this video will be present in the YouTube comment section, and you can also find them on cfstep.com.